In this lecture, we introduce the Poisson process, which is a continuous time analog of the Bernoulli process. One way of thinking about it is as follows. Time is continuous, but conceptually we divide it into a very large number of slots, and during each slot we have a tiny probability of an arrival. This probability is proportional to the length of the slot. Furthermore, we have an independence assumption for the different slots. The Poisson process is a very elegant model of arrival processes in continuous time. It models many real-world phenomena, and it also has a very clean mathematical structure that allows us to calculate practically every quantity of interest. Our development will parallel our analysis of the Bernoulli process. For example, we will find the PMF of the number of arrivals during a time interval and the PDF of the time of the kth arrival. We will discuss the memorylessness properties of the Poisson process. Similar to the case of the Bernoulli process, this is just a consequence of the independence assumptions that we are making. We will then exploit these independence properties to argue that the inter-arrival times are independent exponential random variables, and we will conclude with a comprehensive example. We now set out to study the Poisson process, which is a continuous time version of the Bernoulli process. In the Bernoulli process, time is divided into slots, and during each one of the slots we may either have an arrival or no arrival. In the Poisson process, time is continuous, and we may get arrivals at any time. We want to define the Poisson process by introducing some assumptions that in some ways parallel the assumptions that we made for the Bernoulli process. What were those assumptions? The first one we made was the assumption of independence, namely that what happens in different slots are independent. Similarly, for the Poisson process, we will make the following independence assumption. If we consider two time intervals that are disjoint, and look at the random variable that stands for the number of arrivals during this interval and that interval, we will assume that these two random variables are independent. But even more than that, if we take any collection of disjoint time intervals and we look at the associated random variables, the associated numbers of arrivals, that collection will also consist of independent random variables. The second assumption for the Bernoulli process was one of time homogeneity. Namely, at each slot we had the same probability of an arrival. We want to make a similar assumption for the Poisson process, and it's going to be the following. The probability that we have k arrivals during an interval of a certain duration tau is going to be the same no matter where that interval sits. So, if this is an interval that has a certain duration and this is an interval that has the same duration, the probability of 3 arrivals in this interval is going to be the same as the probability of 3 arrivals in that interval. And therefore, since this probability does not depend on where the interval sits, that probability will be fully defined by the number of arrivals that we're interested in and the length of the interval as opposed to the location of the interval. So we will be using this notation here to indicate this probability. In this notation, we think of tau as a constant, and then P of k corresponds to probabilities. In particular, if you add over all k's, the various probabilities, what you should get would be a value of 1 because this exhausts all the possibilities. And k here ranges from 0 to infinity because we allow an arbitrarily large number of arrivals during a given time interval. Now, with this assumption in place, it would still be possible to have arrivals that happen simultaneously, multiple arrivals at the same time point. In order to avoid this situation, we introduce one more assumption, which is the following. It talks about the number of arrivals during a time interval that has a small length delta. During a small time interval, there is negligible probability of having more than one arrival. We will either have 1 or 0 arrivals, And the probability of one arrival is a certain number, lambda times delta. It's proportional to delta. So if the interval becomes smaller and smaller, that probability also goes to zero, but it goes to zero at a rate proportional to delta. So you can think of lambda as probability per unit time. These are the units of lambda. Now, here I'm writing an approximate equality. What does that mean? It means that these are not exact expressions, but they are exact within a second order term. And the second order term is a term that's negligible compared to the first order term when delta is small. More precisely, mathematically, what we mean is that a second order term compared to a first order term goes to zero as delta goes to zero. Finally, let me reiterate that lambda should be interpreted as an arrival rate. It is a probability per unit time. The bigger lambda is, the bigger the probability is that we get an arrival during a small time interval. If we double lambda, then we double the probability that we have an arrival during a small time interval, and so we expect to have about twice as many arrivals, hence the interpretation as an arrival rate. We will see shortly that this is also justified because lambda shows up in expressions for the expected number of arrivals during a time interval. In what kind of situations does the Poisson process arise? In general, it arises whenever we have events like arrivals that are somewhat rare and which happen in a completely uncoordinated manner so that they can show up at any particular time. In such situations, the number of arrivals will be often described by a certain distribution called the Poisson distribution, and which is named after the person who first studied this situation, who is a famous French mathematician by the name of Siméon Denis Poisson. An early example where the data seems to fit the description of the Poisson process is a curious one. It had to do with deaths from horse kicks, that is, accidental deaths, in the Prussian army. The idea here is that a death by a horse kick can happen pretty much at any time, and different arrivals, that is, different accidents, are completely uncoordinated from each other, so the process is sort of completely random. For more scientific applications, it was realized that certain physical phenomena obey the Poisson process. Examples are the following. You have some radioactive body which decays, and the decay happens by once in a while emitting various particles. Different particles get emitted at completely random times in a completely uncoordinated manner, and therefore this process is actually described as a Poisson process. Conversely, if you have a photodetector who looks at a very weak light source, so photons arrive from that weak light source one at a time, and you look at the times at which photons hit the photodetector, then the process of photon arrivals is very well modeled by a Poisson process. For more modern applications, if you look at the financial markets and the times at which certain very unexpected events, like certain market shocks, occur, a model that is commonly employed is to use a Poisson process model. Although this is not an entirely accurate model, it provides a first approach to situations like this. But these days, the predominant source of applications for the Poisson process is in various service operations. You are the phone company. Phone calls get placed at random times, and because there are several people involved who are uncoordinated with each other, those calls get placed at completely random times. And the same story goes about, let's say, service requests to a web server, service requests to any kind of company. So many applications that are being studied these days and which rest on Poisson models involve service operations of this type. The definition of the Poisson process gives us information about the probability that we get k arrivals during an interval of length delta when delta is a very small number. How can we find the probability of k arrivals during an interval of some general length tau, where tau is no longer a small number? In particular, we're interested in the random variable, denoted n sub tau, which stands for the number of arrivals during an interval of length tau, and we wish to find the PMF of this random variable, the probability that n sub tau is equal to k, and which is what we have been denoting by this particular notation in the context of the Poisson process. Now, if instead of the Poisson model we had the Bernoulli process model, we would know the answer. S, the number of successes or number of arrivals in n slots, has a PMF which is given by the binomial formula. Can we somehow use what we know about the Bernoulli process to find the answer for the Poisson process? The answer is yes, and it involves a limiting argument of the following kind. We take the interval from 0 to t and divide it into a very large number of intervals, so many of them, where each one of the intervals has a length of delta, where delta is a small number. And to push the analogy with the Bernoulli process, we will be calling those little intervals as slots. Now, during each slot, we may get 0 arrivals, 1 arrival, but there is also the possibility that there may be 2 arrivals, or even more than 2 arrivals, happening during one of the slots. Because of this, the picture that we have here is not quite the same as for the Bernoulli process, because in the Bernoulli process, each one of the slots we get only 0 or 1 arrival. So the source of the discrepancy between the two models is that here a slot may obtain 2 or more arrivals. But how likely is this? Let us look at the probability that some slot, that is any one of the slots, contains 2 or more arrivals. That is, we're dealing with the union of the events that slot I has 2 or more arrivals. This event is the union of these events, and therefore the probability of this event is less than or equal than the sum of the probabilities of the constituent events. This is an inequality that we have seen at some point in the past, and we're calling it the union bound. Now, what is this summation? I ranges over the different slots, and we have tau over delta slots, so there's so many terms that are being summed. Now, during any particular slot, the probability of 2 or more arrivals is of order delta squared, according to the definition of the Poisson process, and this quantity converges to 0 when we let delta become smaller and smaller. So this means that the discrepancy between the Poisson and the Bernoulli model, which was due to the possibility that we might get 2 or more arrivals during one of those slots, this discrepancy is something that happens with negligible probability. In other words, the probability that we get k arrivals in the Poisson model is approximately the same as the probability that k slots have an arrival. Since we're neglecting the possibility that some slot has 2 or more arrivals, this means that the number of arrivals in the Poisson model will be the same as the number of slots that get an arrival. This approximate equality becomes more and more exact as we let delta go to 0. But now, what is this quantity? The probability that k slots have an arrival is something that we can calculate using the binomial probabilities. Each one of the slots has a certain probability of having an arrival, and different slots are independent of each other by the defining properties of the Poisson process. Therefore, this approximation that we have developed satisfies the properties of the Bernoulli process. We have a certain probability that each slot gets an arrival, and we have independence across slots.
this means that we can use now the PMF that's associated with the Bernoulli model to calculate this quantity, and then take the limit as delta goes to 0 to obtain a formula for the PMF for the Poisson process. In more detail, what we have is that the number of arrivals, which is approximately the same as the number of slots that have an arrival, obeys a binomial distribution in the limit as delta goes to 0, a binomial distribution in which the probability of arrival during each one of the slots is approximately lambda delta, and the number of slots goes to infinity, and this happens in a way so that the product of the two, n times p, is equal to this term times this term gives us a lambda times tau. This term times this term give us something that's order of delta, so it's negligible. So we have this equality, and so this is approximately lambda tau, with the approximation becoming more and more exact as we let delta go to 0. So all we need to do is to take the formula for the Bernoulli process, use these values of p and n, and take the limit. But this is a problem that we have already encountered and have analyzed. If we let n go to infinity, p go to 0 so that their product stays constant, we have shown that the binomial PMF converges to the so-called Poisson PMF that takes this form. Notice one small difference. N times p here is equal to lambda, whereas here n times p is equal to lambda t. This means that we need to apply this formula, but with lambda replaced by lambda t, and this gives us the final answer. This is the probability of k arrivals during a time interval of length t in the Poisson process, and this is a so-called Poisson PMF with parameter lambda tau. To summarize, our strategy was to argue that the Poisson process is increasingly accurately described by a Bernoulli process if we discretize time in a very fine discretization. And the approximation becomes exact in the limit when the discretization is very fine. So we took the corresponding binomial formula for the Bernoulli process and took the limit that's associated with the parameters that we would obtain if we have a very fine discretization. And this gave us the final formula. Now that we have in our hands the PMF of the random variable n tau, which is the number of arrivals during an interval of length tau, we can go ahead and try to calculate the mean and variance of this quantity. Regarding the mean, we could use just the definition of the expected value and then carry out this calculation, which is not too hard, and in the end we would obtain an answer equal to lambda times tau. This is indeed the correct formula for the expected value, but let us understand why this formula should be true without doing any calculation. Remember that the random variable, the number of arrivals in the Poisson process, is well approximated by a binomial random variable with those particular parameters n and p in the limit when delta goes to 0. And this was through a discretization argument. Therefore, the expected value of n tau should be approximately equal to the expected value that we get from the Bernoulli process, that is the expected value of a binomial random variable. And the expected value of a binomial random variable is n times p, and n times p evaluates approximately to lambda times tau. This second equality here is approximate because we're neglecting this order of delta squared term. Now these approximations are increasingly exact as we let delta go to 0, and when we take the limit as delta go to 0, we see that the expected value of a number of arrivals in the Poisson process will be equal to lambda tau. For the variance, we can follow a similar argument. First, do a binomial approximation and use the formula for the variance of a binomial random variable. And then, when delta is small, This number p is small and it's negligible compared to 1. N times p is approximately lambda t, and so we obtain this expression. This expression here is the correct one. If we were to use the formal definition of the variance and carry out the calculations using the PMF, this is what we would obtain, except that it would be somewhat tedious. The formulas that we have derived, at least the first one, is quite intuitive and has a natural form. The expected number of arrivals is proportional to tau. If we double the length of the time interval of interest, we expect to see twice as many arrivals. This formula also reinforces the interpretation of lambda as an arrival rate. Since lambda is the expected number of arrivals divided by the length of time, it is really the expected number of arrivals per unit time. So it is natural to call lambda the arrival rate or the intensity of the arrival process. Finally, regarding the variance, it is a curious fact that the variance turns out to be exactly the same as the expected value, and this is a special property of the Poisson PMF. We will now go through a very simple example in which we just get to use the formulas that we have available. The Poisson process is a pretty good model of email arrivals, at least during a limited part of the day. For example, during daytime, emails may be arriving as a Poisson process with a certain rate, but then during nighttime, they may be arriving as a Poisson process with a different rate. Nevertheless, the assumption that we will make is that, at least for this problem, that emails arrive as a Poisson process with a fixed rate of 5 messages per hour. What is the mean and the variance of the number of emails received during a day? Well, we have formulas for the mean and the variance, and in this problem we have a lambda equal to 5 and tau consists of 24 hours, so the answer is 5 times 24. And this answer applies to both the mean and the variance because for the Poisson random variable, these are the same. What is the probability that we get one new message in the next hour? This has to do with the PMF of the number of arrivals during the next hour, and that PMF is given by the Poisson probabilities. We're asking for the probability of one new message, so that k is equal to 1, in the next hour, so that tau is equal to 1. So we're looking for this expression here, and using also that lambda is equal to 5, we enter those numbers in this formula, and what we obtain is 5 times e to the minus 5. Finally, what is the probability that during each of the next 3 hours you obtain 2 messages? So this is an event which is actually the intersection of 3 events. The event of 2 messages in this hour, 2 messages in this hour, and 2 messages in that hour. For the Poisson process, we have assumed that different time intervals are independent of each other, so what we need to do is to multiply the probability of 2 messages in this hour with the probability of 2 messages in that hour and the probability of 2 messages in that hour. On the other hand, for each one of the hours, the probability is going to be the same, so it's enough to take the probability of 2 messages during this hour, which is, in our notation, this quantity, and multiply it with itself 3 times, so we get the third power of this. Now, this expression is equal to the following. Lambda times tau is 5, k is equal to 2, so we get 5 squared. Then we have an e to the minus 5 term, and k is equal to 2, so we're dividing by 2, and we take the third power of this. We now follow a program that parallels our development for the case of the Bernoulli process. We will study the time until the first arrival, a random variable that we denote by T1. We're interested in finding the probability distribution of this random variable, and later on we will continue and try to study the time until the kth arrival. Now, T1 is a continuous random variable because the Poisson process runs in continuous time and therefore it has a PDF. But instead of finding the PDF directly, we will first find the CDF of this random variable. So we fix a certain time t and we're asking for the probability that the first arrival happened during this interval. Now this is 1 minus the probability that the first arrival happened outside this interval. So we can write this probability as 1 minus the probability that t1 is bigger than t. But what is this event? The first arrival occurring after time little t is the same as saying that there were no arrivals in the time interval from 0 to little t. And this probability of 0 arrivals in a time interval of length t is something for which we already have a formula. Take this formula and replace k by 0, tau by t. When k is equal to 0, this term is something to the 0th power equal to 1. Using our convention that 0 factorial is equal to 1, we're left just with e to the minus lambda t, and this is the answer for the CDF of the time until the first arrival. We then take the derivative, and we find that the PDF of the time until the first arrival has this form, which is the PDF of an exponential random variable. Of course, this calculation here is only valid for t's that are non-negative. For negative t's, the PDF of t1 is of course 0. For the exponential random variable, we have seen that it has certain memoryless properties. Namely, if I condition on the event that nothing has occurred until a certain time t, and I'm interested in the time from now until the first arrival occurs, this remaining time until the first arrival is again an exponential distribution. That is, looking ahead from this time, I will still wait an exponentially distributed amount of time until I see the first arrival. Whatever happened in the past and how long I have been waiting doesn't matter. Starting from this time, I will still wait an exponentially distributed amount of time. This is essentially an expression of a fresh start property of the Poisson process, which is analogous to the fresh start properties for the Bernoulli process, and we will be discussing this fresh start property a lot more. Having figured out the distribution of the time of the first arrival, let us now study the time of the kth arrival, a random variable that we denote by y sub k, similar to the case of the Bernoulli process. This random variable is a continuous one because arrivals happen in continuous time, so it takes continuous values, and therefore it will be described by a PDF, and this is what we want to find. In order to find it, we will make use of the Poisson PMF that we have already derived for the number of arrivals during an interval of a fixed length. One approach to finding the PDF of yk is the usual program, similar again to what we did for the case of the first arrival time. We can first find the CDF and then differentiate to find the PDF. So what is the CDF? We want to calculate the probability that yk is less than or equal to some number little y. Now, what is this event? The kth arrival occurs by time y. This means that by time y, we've had at least k arrivals. We've had k arrivals, or maybe k plus 1, or maybe k plus 2. We've had some number of arrivals, n, in an interval of length y, and this is an event that happens with this probability, but we need to take into account all the possible values of n that are at least as large as k. Now, we have a formula for this probability, the probability of n arrivals in an interval of given length. This is the Poisson PMF with appropriate changes of symbols. So we can take this expression, substitute it here, and then differentiate, do some algebra, and find the answer. Instead of carrying out this algebra, however, we will proceed in a more intuitive way that will get us there perhaps faster. And the derivation that we will follow actually parallels the one that we went through in the case of the Bernoulli process. The intuitive argument that we will use will rest on the interpretation of a PDF in terms of probabilities of small intervals. So the PDF evaluated at some particular point y times delta is approximately the probability that our random variable falls within a delta interval from this number little y that we are considering. So here times 0, here's time y, and here's time y plus delta. We want to find or to say something about the probability of falling inside this small interval. Now, what does it mean for the kth arrival to fall inside this interval? This is an event that can happen as follows. The kth arrival falls in this interval, and we've had k minus 1 arrivals during the previous interval. What is the probability of this event? A basic assumption about the Poisson process is the independence assumption. Therefore, having k minus 1 arrivals in this interval and having 1 arrival in this interval are independent events. Therefore, the probability of this scenario is the product of the probabilities that we've had k minus 1 arrivals in an interval of length y times the probability that we've had one arrival in an interval of length delta. And that latter probability is approximately equal to lambda times delta. So I should write here an approximate equality instead of an exact equality to indicate that there are other terms, order of delta squared for example, but which are much smaller compared to delta. However, this is not the only way that we can get the kth arrival in this interval. There's an alternative scenario. We might have had k minus 2 arrivals during this interval and then 2 arrivals during that little interval. In this case, the kth arrival again occurs within that little interval. So we need to also calculate the probability of this scenario. The probability of that scenario is the probability of k minus 2 arrivals in an interval of length y times the probability of 2 arrivals, but the probability of 2 arrivals is something that's order of delta squared. And order of delta squared is much smaller than this term, which is linear in delta, and so this term can be ignored as long as we're just keeping track of the dominant terms, those that are linear in delta. And then they would be similar expressions. For example, the scenario that we have 3 arrivals up to time y and then 3 more arrivals during that little interval, which is again an event of probability order of delta squared, that we get 3 arrivals there. And all of those terms are insignificant and we can ignore them. And we end up with an approximate equality between this term and this expression here. Delta shows up on both sides, so we can cancel delta. And therefore, we have ended up with a formula for the PDF. In particular, the PDF is equal to this probability times lambda. What is this probability? We have a formula for it, but we just need to substitute, put k minus 1 in the place of k, and put a y in the place of tau. This gives us lambda y to the power k minus 1 e to the minus lambda y divided by k minus 1 factorial. And then we have the extra factor of lambda, which can be put together with this lambda to the k minus 1 here, and we end up with this final formula for the PDF of yk. The distribution that we have here is called an Erlang distribution, but actually it's not just one distribution. We have different distributions depending on what k we're considering. The distribution of the time of the third arrival is different from the distribution of the 10th arrival. So if we fix a particular k, then we say that we have an Erlang distribution of order k. For the case where k is equal to 1, this term here disappears, k minus 1 is equal to 0, and the denominator term disappears, and we end up with lambda times e to the minus lambda y. But this is the exponential distribution that we had already derived with a different method earlier. As you increase k, of course, you get different distributions, and these tend to shift towards the right. This makes sense. The time of the second arrival is likely to take certain values. The time of the third arrival is likely to take values that are higher. And the more you increase k, the more the distribution will be shifting towards the right. This segment is probably the most critical one for the purpose of understanding what the Poisson process really is and how it behaves. There will be almost no mathematical formulas, but the segment will be quite dense in terms of conceptual reasoning. So pay a lot of attention. In a nutshell, we will argue that the Poisson process has memorylessness properties that are entirely similar to those that we have seen for the Bernoulli process. This should not be surprising, since the Poisson process can be thought of as a limiting case of the Bernoulli process. We will reason through these properties not in the style of a formal mathematical proof, but with an intuitive argument. But I would like to assure you that the intuitive argument can be translated into a rigorous proof. The first property is the following. The process starts at time 0. You come in and start watching at, let's say, time 7. Or more generally, instead of time 7, suppose that you come in and start watching at some time little t. The important thing here is that little t is a constant. It's a deterministic number. Starting at that time, what will you see? Well, the original process was Poisson. This means that disjoint intervals in the original process are independent. Therefore, disjoint intervals in the process that you will be seeing will also be independent. Furthermore, during any little interval of length delta in the process that you see, we still have probability lambda times delta, approximately, of seeing an arrival. Therefore, what you see also satisfies the properties of a Poisson process and is itself a Poisson process. Second, the original process was Poisson, so different intervals are independent. So whatever happens in this interval is independent from whatever happens in that interval, but that interval corresponds to the future of the process, and therefore the future of the process, what you get to see, is independent from the past history. And so the conclusion is that the process that you get to see is a Poisson process, which is independent of the history until the time that you started watching. And we say, therefore, that what you see is a fresh starting process. The Poisson process starts fresh at time t. We have the fresh start property. And similar to the language we use for the Bernoulli process, the fresh start property means that you see a process that's independent of the past and which has the same statistical properties as if this was time 0, as if the process was just starting right now. One consequence of this fresh start property is the following. You start watching at time t, and you're interested in the time it takes until the next arrival. What are the properties of this random variable? Well, since you have a fresh starting Poisson process at this time, this is the time until the first arrival in this fresh starting Poisson process. And the time until the first arrival in a process that is just starting, we know that it has an exponential distribution. So this is going to be an exponential random variable with the same parameter lambda. Furthermore, because the process starts fresh, whatever happens in the future is independent from the past, and so this random variable, the remaining time, is independent of whatever happened in the past until time t. Now let us look at a somewhat different situation. You start watching the process at time t1. Time t1 is the time of the first arrival. And you start watching from here on. What is it that you're going to see? Suppose that the first arrival happened, let's say, at time equal to 3. so we're conditioning on this event. In that case, you start watching the process at time 3, and you also know that the first arrival happened at time 3. But this fact about the first arrival happening at time 3 belongs to the history of the process until time 3. This is information about the past and does not affect what is going to happen after time 3. The process after time 3 will be independent from the history until time 3 and whatever happened until that time. So starting at that particular time 3, what you see is a Poisson process that is independent from the past. Now, this argument is valid even if I were to use here a 3.5 or 3.4 or 3.7. No matter when this first arrival occurred, what I see starting from this time is a Poisson process which is independent from the past. At the time of the first arrival, the process just starts fresh. As a consequence of this, and by repeating the argument that we carried out for the remaining time until the next arrival up here, we can repeat this argument and argue that the time until the next arrival in this fresh starting process, this will also be an exponential random variable. Now, this time until the next arrival is the difference between the second arrival time and the first arrival time, and we denote it by t2. What we just argued is that this time until the next arrival is going to be an exponential random variable, and also it is independent from the past, and in particular it is independent from t1. So the time until the second arrival, starting from the first arrival, the second inter-arrival time is a random variable that has an exponential distribution that is the same distribution as that of t1 and is independent from t1. Now we can extend this argument and look at the kth inter-arrival time. For example, if the arrival numbered k-1 occurred here and the kth arrival occurs here, this difference here we denote it by tk, and by arguing in a similar way that the process starts fresh at this particular time, the time until the next arrival will also be an exponential random variable with the same distribution, and furthermore will be independent from the past history and therefore independent from the earlier inter-arrival times. And this has lots of important implications. For example, the time until the kth arrival, which is the sum of the first k inter-arrival times, is a sum of independent, identically distributed exponential random variables. In particular, this means that we can find the PDF of yk by convolving the exponential PDF of these inter-arrival times, convolving this exponential PDF with itself k times. And this is indeed one way to find the PDF of yk. But fortunately for us, we were able to find it with a much simpler argument, and we already know what it is. But this property here is also useful for finding the mean and the variance of yk. The mean of the sum is the sum of the means, and since the random variables are independent, the variance of the sum is the sum of the variances. We know what is the mean and the variance of an exponential, and so by multiplying that by k, we obtain the mean of the kth arrival time and the variance of the kth arrival time. And so we now know the mean and variance of the Erlang PDF of order k. A second implication of this property is more theoretical, more conceptual. Recall that we defined the Poisson process in terms of an independence assumption and an assumption on the probability of arrivals during a small interval. But we could have defined the Poisson process as follows. Consider a sequence of independent identically distributed exponentials, call them tk, and use these to define the arrival times. This is a way of constructing a process. What we argued in this segment is that a Poisson process under the original definition satisfies this new definition. One can complete the argument to show that the two definitions are equivalent. It is possible to argue that if we define an arrival process in this manner, this arrival process will also satisfy the basic properties of the Poisson process. This argument can indeed be carried out, but we will not go through it. And final implication, which is a little more practical. If you want to simulate the Poisson process, how would you do it? Given what we now know, the most natural way is the following. We generate independent, identically distributed exponential random variables using, for example, a random number generator, and then use these exponential random variables to construct the values of the interarrival times, and this way construct a complete time history of the Poisson process. Let us now take stock and summarize what we have done for these two processes, the Bernoulli and the Poisson process and their relation. The Poisson process runs in continuous time, whereas for the Bernoulli process, time is discrete and is divided into slots. The Poisson process is defined by a single parameter, lambda, which is the intensity or arrival rate, and tells us the expected number of arrivals per unit time. For the Bernoulli process, we have again one basic parameter, which is the probability of success at any given trial, or the probability of an arrival during each one of the slots. Based on our model, we were interested in three kinds of quantities, and we found the distributions of them. The first quantity is the number of arrivals during a certain time interval. For the discrete case, the number of arrivals has a binomial distribution, whereas for the Poisson case, the distribution is that of a Poisson random variable. Then we looked at the time until the first arrival, or the time between consecutive arrivals. For the Bernoulli process, that distribution is geometric. For the Poisson process, that distribution is exponential. Note that in this instance, we're dealing with a discrete random variable, but here with a continuous random variable. And then, as a generalization, we could find the time until the kth arrival, which in the Poisson case is given by an Erlang distribution, and for the Bernoulli case we developed one particular formula, and that formula is actually known under the name of a Pascal distribution. All of these results for the Poisson case were obtained because we used an approximation argument. That is, we had the results for the Bernoulli case, but then we argued that the Poisson process is a limiting case of the Bernoulli process, in which we take time, divide it into a large number of slots. During each one of the slots, however, we have a small probability of an arrival, and this is done in a way so that the product of these two numbers stays a constant. By using a finer and finer discretization, we could approach the Poisson process arbitrarily close by a Bernoulli process, and then we used the Bernoulli formulas in which we took the limit as delta was going to 0, and this gave us the result for the Poisson case. In this segment, we go through an example to get some practice with Poisson process calculations. The example is as follows. You go fishing and fish are caught according to a Poisson process with an arrival rate, that is the rate at which fish are caught, of 0.6 fish per hour. You will fish for 2 hours no matter what. And if during those 2 hours you have caught at least one fish, then you stop. As in this scenario, in which you have caught 3 fish during the first 2 hours and then you stop. Otherwise, you will continue until you catch one fish, and at that time you will stop. We will answer a few questions, and we will write down the answers to these questions in terms of the notation that we have introduced, and here for reference we have all the formulas that we have developed so far. The first question is, what is the probability that you get to fish for more than 2 hours? Well, you get to fish for more than 2 hours if and only if you didn't catch any fish during the first 2 hours. So this is the probability of catching 0 fish in the first 2 hours. And we can use this formula, substitute k equal to 0, tau equal to 2, lambda equal to 0.6, plug in the numbers and obtain a numerical answer. We will not bother the numerical answers, we will just be writing down the expressions that give us the answers. Now, in this question, we could have a different approach. You will fish for more than 2 hours if and only if there are no arrivals during the first 2 hours, which means that the first arrival in the Poisson process of fishing happened after time 2. So we're talking about the event that the first arrival, T1, is bigger than 2, and we're looking into the probability of this event, which is the integral of the density of the first arrival time, and the integral is taken over the range of values of interest larger than 2, that is from 2 to infinity. We know that this density is exponential, so we can write down this integral and evaluate it. So notice the difference between these two approaches. Here we think in terms of the random variables that correspond to the number of arrivals during a certain time interval. Here we're reasoning in terms of interarrival times. And more generally, for Poisson process problems, an event of interest sometimes can be expressed in terms of number of arrivals, or sometimes it can be expressed in terms of arrival and interarrival times, or sometimes both approaches are possible. But usually one of the two approaches will be simpler than the other. For example, here we already have a formula, whereas here we would need to evaluate an integral. Here is now our next question, which is a little bit more complicated. What is the probability that you get to fish for more than 2 hours and also you get to fish for less than 5 hours? This is the scenario, again, that you fish for more than 2 hours, which means that no fish were caught during the first 2 hours, and then you continue fishing, and by time 5, you have already caught your fish and you have left. Now, it is convenient of thinking about the Poisson process as follows. Think about the Poisson process of catching fish at a rate of 0.6 per hour as going on forever. So there's a fisherman who fishes forever, except that this fisherman at either this time under this scenario or at that time under this scenario raises a flag and says, okay, this is the time I should be stopping. So, even though the fisherman will stop fishing at this time, we can imagine that the Poisson process keeps going on. With this way of thinking, the fact that you stopped fishing before time 5 is the event that the number of fish caught, or the number of Poisson arrivals during the interval from 2 to 5 is at least equal to 1, larger than or equal to 1. So the event of interest consists of the intersection of two events. 0 fish caught during the first 2 hours, which has this probability, and at least one arrival in the Poisson process between times 2 and 5. This is a time interval of length 3, and having at least one arrival is 1 minus the probability of 0 arrivals in a time interval of length 3. Notice that I'm multiplying those two probabilities here. Why am I doing this? In a Poisson process, whatever happens in disjoint time intervals are independent events. So an event having to do with this interval, the event that no fish were caught, and the event that has to do with this interval, at least one fish caught, at least one arrival during this time interval, these two events are independent, and this is why we can multiply their probabilities. Now let us think of the alternative approach, a different way of describing this event using arrival and interarrival times. What is this event? This is the event that no arrival happened until this time, but an arrival happened before time 5. So this is the event that the first arrival happened after time 2, but before time 5. and we're looking at the probability of this event, which we can find by integrating the PDF of the first arrival time from 2 until 5. The next question is, what is the probability that we catch at least 2 fish? Under this scenario, we catch 1 fish and we stop. Therefore, this scenario must have materialized. The event of catching at least 2 fish is the scenario that from time from 0 until 2, we caught at least 2 fish. So we're talking about the probability of catching at least 2 fish, which is the probability of catching k fish during a time interval of length 2, where k can be anything from 2 to infinity. So this is the probability that the number of fish caught during these 2 time units is at least equal to 2. And an alternative way of writing this expression so that we do not have to evaluate an infinite sum, it is 1 minus the probability of catching 0 fish and minus the probability of catching 1 fish. If we were to write this in terms of arrival and inter-arrival times, we will catch at least 2 fish if and only if, by the time we stop, which will be time 2, we've had 2 arrivals, which means that the second arrival time happened before time 2. So we're looking into the probability that the second arrival time happened before time 2, which is the integral from 0 to 2 of the density of the second arrival time. We have a formula for this density given by the Erlang PDF, so we could take this expression, plug it in here, evaluate the integral, and obtain the same answer as we would have obtained here. Clearly, in this case as well, this first approach would be a simpler one because these probabilities are already available to us. The next question is the following. Suppose that you already fished for 3 hours. This is something that can only happen under this second scenario. So no fish have been caught until time 2, you continue, no fish were caught until time 3. And given that this event has occurred, what is the expected value of the future fishing time? The expected value until a fish gets caught for the first time. Well, the Poisson process starts fresh at time 3. No matter what happened in the past, no matter what information were given in the past, now you're sitting at time 3 and looking into the future, you have a fresh starting Poisson process as if this was the initial time. Starting from this time, the time until the first arrival is going to have an exponential distribution with parameter lambda, and the expected value of this distribution is equal to 1 over lambda. Finally, let us look at a different type of question. What is the expected value of the total time that you get to fish? Let us introduce here some notation. Let us call the total fishing time capital F, and the total fishing time consists of 2 pieces. There's the time until time 2 that you will be fishing no matter what, and then there's going to be the remaining fishing time after time 2. So now let us look at the expectation of the remaining fishing time after time 2. Here there are 2 scenarios. In the first scenario you stop, in the second scenario you continue, and we will take into account these 2 scenarios by using the total expectation theorem. The first scenario happens with some probability. This is the probability that you stop fishing at time 2. And in that case, your remaining fishing time is going to be equal to 0 because you do not continue under that scenario. But there's the other scenario that you get to fish for more than 2 time units, and then we multiply this term with the conditional expectation of the remaining fishing time, given that you got to fish for more than 2 time units. So what is this term? The probability that you get to fish for more than 2 time units, this is the probability that no fish were caught during the first time units. This is the probability of the second scenario. And then we have this conditional expectation. Given that you didn't catch anything, and therefore you will be continuing fishing, what is the expected amount of time, f minus 2, that you will be fishing? Now, the Poisson process starts fresh at time 2, so looking into the future, we're faced with the Poisson process and we're asking for the expected time until the first arrival. And this time has an expected value equal to 1 over lambda. Our last question is of a similar type. What is the expected number of fish you are going to catch? Once more, we will break this into 2 pieces. Number of fish caught during the first 2 hours and number of fish caught during the remaining hours. During the first 2 hours, the expected number of fish that you catch is given by this formula. It is equal to lambda tau, and in our case, lambda is 0.6 and tau is equal to 2, plus the expected number of fish that are caught afterwards. What is this expected value? Again, we think in terms of the total expectation theorem. There's one scenario that has a certain probability, and under that scenario, you do not catch any fish, so that doesn't give us any contribution. Then there is this scenario, the second one, that has this probability of occurring, the probability of catching no fish here, so that the second scenario materializes. And if that second scenario materializes, how many fish are you going to catch after time 2? It's going to be 1 fish with certainty. And this is the final answer to this question. Notice that in answering both of these questions, we use the divide and conquer strategy twice. We first divided the time horizon into 2 pieces and dealt separately with each one of the pieces. And then, in order to deal with this second piece, the time after time 2, we use divide and conquer into the 2 different scenarios and using the total expectation theorem.